Good morning, my dear friends. So we studied about theory of damping system. Okay, now in this class, I'm going to solve three different types of problem. Okay, so that is problems on damping system. Okay, so I told you damping. What do you mean by damping, and what are the different types of damping, and when we are going to call as over damp system and under damp system and critical damp system. Okay, so before this, I told you in the last class. So what are the symbols we are going to use while solving the damping system problem? Okay, and the list of formula also we studied. Okay, so now first problem. Okay, so here very simple problems on damping system. Okay, just you have to remember what are the symbols and what are the notations and what are the list of formulas. Okay, so here after remembering those points, just you read the question and where to, how to apply and where to get the answer. Okay, that you have to understand. Okay, so I will read out here the first problem. So calculate or the determine the critical damping coefficient. Okay, I already told you critical damp system coefficient notations and what are the symbols. Okay, and second one is the damping factor, natural frequency of the damped vibration. Okay, fourth one is the logarithm decrement, and fifth one is the ratio of the consecutive amplitude of the vibrating system. Okay, which consists of a mass of 25 kg and the spring stiffness is 15 kilonewton per meter and the damper. Okay, so the damper is provided is only the 15% of the critical value. Okay, so I told you critical damping coefficient is denoted by Cc, damping factor is denoted by zeta, natural frequency is denoted by omega n. Okay, ratio of successive amplitude is equal to x1 by x2. Okay, these points, these are the symbols we are going to call particular definitions. Okay, that you have to remember while solving the problem. Okay, so here they given what the damping is provided is only the 50% of the critical value. Okay, so you need to calculate what the Cc and damping factor zeta, all those things. Okay, so here they given in the question. Okay, mass of the particular system is given, that is m is equal to 25 kg and k stiffness is given 15 kilonewton per meter. Okay, so this is in terms of kilonewton, kilo is given, so you convert into newton per meter only. You may get one standard form, that is SI unit. Okay, so read the question carefully, that is twice thrice, and note down the given data what they given. Okay, so here four quantities given. One is mass, stiffness, damping of 15% of the critical damping. Okay, so we know that that is C by Cc. Okay, that is 55% is equal to that is what 0.15 divided by 100. Okay, these are the four quantity they given in the given question. Okay, so just we know that the natural frequency formula is equal to what, so square root of k by m. Okay, we know that k is equal to m. Okay, we know that k value they given 15 into 10 to the power of 3 divided by 25. Just to substitute, we are going to get what, omega n is equal to 24.49 radian per second. That is what unit of that natural frequency. Okay, so first one is critical damping coefficient, it is denoted by Cc. Okay, we know that the formula Cc is equal to what, critical damping coefficient formula is Cc is equal to 2m omega n. Okay, mass we know, and omega n is also we know that. Just to substitute, we are going to get what, Cc is equal to 1224.7 newton second per unit. Okay, so mass is given 25, omega n is equal to already we calculated 24.49. just to substitute, we are going to get. Okay, so second one is damping factor. Okay, damping factor, it is denoted by zeta and is given by ratio of C by Cc. Okay, so we know that C is equal to what, they given C is equal to 15% of Cc. Okay, just to 15% of Cc, just to substitute, Cc will get cancelled. Okay, we got what, zeta is equal to 0.15. Okay, so next one is the natural frequency of the damped vibration, that is denoted by omega d. Okay, so already I told you the formula of omega d is equal to what, omega n into square root of 1 minus zeta square. Okay, we calculated omega n, zeta also we calculated. Okay, just to substitute, we are going to get omega d is equal to 24.22 radian per second. That is a damped vibration. Okay, so last, that is the fourth one is the logarithm decrement. Okay, that is denoted by delta. Don't make confuse here, the damping is denoted by zeta and logarithm decrement is denoted by delta. Okay, so here the logarithm decrement delta is equal to what formula, we know that here the logarithm decrement formula is, there are three different types of formula. Okay, but here they given in terms of, we know that the zeta value. Okay, that you take the formula. Okay, delta is equal to 2 pi zeta divided by square root of 1 minus zeta square. Okay, just to substitute all the values here, 2 pi into zeta is equal to 0.15. Okay, square root of 1 minus 0.15 square. Okay, so delta is equal to what, 0.953 is a logarithm decrement. Okay, so and last also they are asking what, ratio of the two consecutive amplitude, that is x1 by x2 is equal to what. Okay, again the logarithm decrement formula we know that what, delta is equal to ln of that is x1 by x2. Okay, so x1 divided by x2 is equal to e to the power of delta. Okay, so we know that delta is equal to 0.95 already we calculated. Okay, just to substitute e is equal to 0.95, so we are going to get what x1 by x2 is equal to 2.594 is the ratio of the two consecutive amplitude. Okay, so like this we have need to calculate. Okay, this is very important problem, they may ask you on 8 marks question in the examination. Okay, so I hope you understand. Here nothing much is there, just to remember the list of formulas. Okay, so now I'm going to solve another problem, that is the second problem. So I will wrote here. So when the vibrating system consists of a mass of 50 kg, spring stiffness 30 kilonewton per meter, and a damper. Okay, damping is 20% of the critical value, so that you are going to calculate or determine the damping factor, critical damping coefficient, logarithm decrement, ratio of the two consecutive amplitude. Fifth one is the natural frequency of the free vibration, and sixth one is the natural frequency of the damped vibration. Okay, these are the quantities we are going to calculate with the help of this given data. Okay, so this is about the problem. So note on the first step is write the given data. Okay, so here the particular spring mass damper system mass is given, that is 50 kg, and the stiffness is given 30 kilonewton per meter. Okay, just to convert into newton per meter. Okay, that is converted to kilo. Okay, 30 into 10 to the power of 3 newton per meter. Okay, cc is equal to what? 20% of the cc, that is 0.02 cc. Okay, so that the first one, that is the damping factor, is equal to what? Zeta is equal to c by cc. Okay, so just to substitute that is what 20% of critical damping, so you are going to get zeta is equal to 0.2, that is called as damping factor. Okay, next one is the critical damping coefficient. Okay, cc is equal to, we know that formula 2m into omega n. Okay, we know that mass also we know, omega n is also we know that. Okay, so they just to substitute values, cc is equal to 2 into square root of 50 into 30 into 10 to the power of 3, you are going to get what? Cc, that is critical damping coefficient, is equal to 244.5 newton second per meter. Okay, so next one is the logarithm decrement. Okay, so logarithm decrement also you need to calculate. Delta is equal to what? 2 pi zeta square root of 1 minus zeta square. Okay, just to substitute all those, that is zeta value, you are going to get what? Delta is equal to 1.28, that is called as logarithm decrement. Okay, so once you calculate logarithm decrement, now you have the formula, what? Ratio of the two consecutive amplitude. Formula normally is given by that is a log, that is log of x n divided by 1 minus 1 x n of divided by x n plus 1, or x1 by x2. Okay, so you take that, and delta is equal to, we know that is x1 by x2 is equal to e to the power of delta. Okay, so e to the power of delta is equal to 1.28. Okay, just to substitute, you are going to the ratio of x1 by x2 is equal to 3.60. this is the ratio of two consecutive amplitude. Okay, so now fifth one is the natural frequency of the free vibration. Okay, that is what circular frequency of the free vibration is. We know that omega n is equal to square root of k by m. We know that that is stiffness 30,000 and divided mass is equal to 50. Okay, just to substitute, we are going to get natural frequency is equal to 24.49 radian per second. Okay, so now the natural frequency of the vibration is f of n is equal to omega n by 2 pi. Okay, natural frequency of that is a natural frequency of free vibration omega f of n is equal to omega n by 2 pi. Okay, we know that the natural frequency is 24.49 divided by 2 pi. Okay, so that just to divide by that, you are going to get what? F of n is equal to 3.9 hertz. Okay, so sixth one is the natural frequency of damped free vibration. Okay, f of d is equal to omega d into 2 pi, just to replace where n is there, just to d. Okay, the formula, okay, that is f of d is equal to omega d divided by 2 pi. Okay, so this is equal to omega n square root of 1 minus zeta square divided by 2 pi. Okay, 1 by 2 pi square root of 1 minus 0.2 whole square into 24.44. Okay, therefore damped that is a frequency is equal to what? 3.82 hertz. Okay, so like this you need to calculate the different types of quantities what they ask in the question. Okay, just to remember the formula, that's it. Okay, so here the entire this damping particular system is, you have to remember mass, stiffness, cc, c, delta, x1 by x2. These are the main important symbol we are going to use in this damping particular system problems. Okay, so now I move on to the third problem. Okay, this is also very interesting. So here also a body of a mass of 10 kg, so mass is given 10 kg, is suspended in a helical spring having a stiffness of 2 newton per mm. Okay, that is the stiffness is given k. A damper is having a resistance of 5 newton at a velocity of 0.1 meter per second. Okay, velocity is given. Okay, is connected between the mass and fixed end of the spring. Determine the ratio of successive amplitude and the amplitude of a body after 10 cycle if the initial amplitude is 15 mm. Okay, so this is a question they given. Okay, just to note on the given data, that is k is equal to 2 Newton per mm is given, that is you convert into meter, that is 2000 Newton per meter. Okay, cc, that is c is equal to f into, that is frictional force divided by velocity is given. So 5 by 0.1 is equal to 15 Newton second per meter, that is a damping is given. Okay, mass is given 10 kg and the initial velocity x naught is equal to 15 mm. Okay, these are the four quantities they given in the question. So you need to calculate what critical damping. Okay, we have the critical damping formula, cc is equal to 2m into omega n. Okay, so otherwise 2 into square root of m cube, both formula you can use. Okay, if they given in terms of k means use this formula, if they asking in terms of omega n means you use that formula. Okay, so here we know that mass and k, so cc is equal to, that is critical damping is equal to 2 into square root of 200 into 10. Okay, cc is equal to what, it is a critical damping coefficient is equal to 282.84 Newton second per meter. So this is about the critical damping. Okay, so next one is the damping factor. We know that damping factor is equal to what, the ratio of damping divided by cc, that is critical damping. Okay, just to substitute you are going to get what, zeta is equal to 0.17. Okay, so now the third one is the logarithm decrement. Okay, so logarithm decrement formula we have what, delta is equal to 2 pi zeta square. Okay, 2 pi zeta divided by square root of 1 minus zeta square. We know that zeta value already we calculated in the top, that is 0.17. just to substitute in that, delta is equal to, you are going to after simplify, so you are going to get what, delta is equal to 1.1286. okay, that is about the logarithm decrement. Okay, so here again they given the ratio of the two successive amplitude. Okay, so normally ratio of the two successive amplitude is given by what, x1 by x2 is equal to e into delta. Okay, so we calculate the delta is equal to 1.28, just to substitute in that, x of 1, or you can take x1 by x2 or x of n divided by xn plus 1. Okay, is equal to 3.09. okay, so this is about the ratio of the two successive amplitude. Okay, so now they are in the fourth, they are asking very important. So for the amplitude after 10 cycle, okay, normally 10 cycle means at what the amplitude going to reduce. Okay, how we generate the formula, initial first initial x naught by x10 they given. Okay, is equal to x 0 by x1 into x1 by x2 up to x9 by x10. Okay, so after writing that, x naught by x10 is equal to x naught by x1, okay, to the power of 10 cycle. Okay, therefore x naught by x1 is given 3.09. we already calculated the ratio of two successive amplitude. Okay, 10. So x naught by xn is equal to what, 79735.46. if you multiply that, if you take that value means you are going to get this. Okay, therefore x 10 is equal to x naught by that divided by that. So x naught is initial amplitude is, that is initial velocity is given 15. So just to substitute in that, so you are going to get x10 is equal to 1.8812 into 10 to the power of minus 4 mm. This is the amplitude after the 10 cycle. Okay, so like this you have to calculate. Okay, so I will repeat the last step. If they ask amplitude after 10 cycle means just you make it equal. Okay, x naught by x10 is equal to last one. Okay, x1 naught x10 is equal to, just to take the last. Okay, x naught 1, x naught, that is initial for is the first position to last one, is x0 by x1 to the power of 10. Okay, so this we are going to calculate already, that is the ratio of two successive amplitude x1 by x2. just to substitute you are going to get. Okay, like that you are going to calculate the x10. Okay, so I hope you understand all these three problems. Okay, all these three problems are very important for the point of examination in damping factor. Okay, so now I will stop here. Okay, I hope you understand this. Thank you.